you're going to need this because you're going to be signing some autographs. So here is, you may not be able to make that out, but he is wearing an Aloha shirt. Congratulations.
I said yes, but this was not my idea. Thank you, John.
Thank you.
Should I start? What's it? Shall I go? Yeah. We'll take care of this throughout the rest of the week. Thank you very much. Thank you, John, and thank you everyone for coming. I just wanted to start off with a picture from the before times. This picture was taken in Prague, Czech Republic, about 1 month before the COVID-19 global lockdowns. It was the last, so far until we resume, but currently the last C++ committee meeting. And we just barely finished C++ 20 at that meeting just in time. And as we mentioned at the fireside chat, we've been working virtually ever since. Today, it is 623 days since this picture was taken. And at this event, we have a few dozen people who are in that picture, plus many more of you. And it is the first time that most of us are seeing each other in 3D in almost 2 years. We want to welcome all of you. It is so good to see you and the over 1,000 who are attending and watching live right now with CppCon online as our hybrid conference. Welcome from me personally. It is so good to see you. And it's great that we can meet here safely, so thank you for cooperating with all the measures to make sure that this is an event we can look back on and really enjoy for the social and the technical content. And the other reason I mention this slide is because, as Bjarne mentioned yesterday, C++ 20 really is historic. That's where we finished the work on that standard. It is the third major big release of standard C++ ever. And it's the first one ever to have virtually the entire feature set that Bjarne Stroustrup outlined in the design and evolution of C++ way back in the before times of 1994. And Bjarne talked about that yesterday in his opening keynote. And there's still a unified function call syntax, as he mentioned that we still don't have that one, but other than that, we have all the major features. So one of the questions that comes up is, well, are we done? Is C++ finished? And in the English language, the word done and the word finished both have two meanings. So the answer to both is no. C++ is not finished, nor is it finished. But we are continuing work on C++ 23, which is almost feature complete, and other long-term features, including static reflection, contracts, and pattern matching are among the priorities the committee has selected to work on. And I'm going to talk a bit about pattern matching today. The first thing I want to do is thank all of the folks who've been working for nearly a decade just in C++ for pattern matching, and there are more, but here are some of the major ones. I think 4 are in the room here today. So if your picture is on this screen, and please, could you stand up and wave so people can see you and know where you are? Thank you. Please give them a round of applause. Thank you, Bjarne, David, Sean, and I know I'm missing at least one. We're glad to see you in 3D as well. So thank you for all this work. I'm mainly going to be focusing on the last couple, 1371 and 2392, which is my paper, and the circle implementation you'll see demoed by Sean, who wrote it. So let's start with an overview of why are we talking about this pattern matching thing at all? Can't we just use if? If is pretty good. And then I'm going to talk about some general design questions that also influence how we view C++ evolution. So let's start with looking backwards into the 1970s. Why did Dennis Ritchie include switch? And I don't think he was the first, but C had switch. Why did he include that when he already had a perfectly good if? The code on the left and the right do the same thing, right? They do, if you write it carefully. So why do we have switch in the language? Well, there are two good reasons that resonate with me. One is expressiveness. I can directly express my intent. And this is subtle, but I think it is really, really important. On the right-hand side, as soon as you, as the human, or as the compiler, reads the word switch, without looking one character further, you know exactly what's coming. You know that the thing that comes next is going to be evaluated exactly once, and then tested potentially multiple times with the same value. And you know that because you said a word, switch, that is a word of power, that tells you upfront exactly what to expect. Now, on the left-hand side, the if cascade will do the same thing, but you have to get single evaluation, you may have to take the complex expression and evaluate it once yourself, and then use that result explicitly, create a temporary. And when I see the word if, even when I see x equals 0, I don't know without reading further, are these going to be exclusive cases? Am I really testing one value at a time? Did I write a bug? Because if I do it that way, I can write the bug, even if I meant to test one value at the time. And it's good for efficiency because this is typically easier for tools to optimize. So here is an example that's taken from an LLVM optimization. I happen to be using the Circle compiler, the C++ compiler that Sean wrote with LLVM as a backend. These optimizations are LLVM optimizations. Clang will do the same thing. So on the left, I have a switch cascade. Switch break case 0, break case 1, break case 2, break default. And on the right-hand side, in the generated assembler, you can see the ifs, the test jump equal, comp jump equal, comp jump not equal. There's my if cascade, transliterated one for one. But you'll notice that I commented out on line 13, and I commented out case 3. It turns out on LLVM, as soon as you have 4 cases in a row or more with consecutive values, we don't generate an if cascade. We don't generate a bunch of jumps. We generate exactly one jump that uses a jump table, which is just a hard-coded list of addresses. And yes, there is a bounds check. That's on assembler line 2. So you want a bounds check for your jump table for sure, but not to get a wild branch. But now I do a single jump, and that's an optimization you could do for the if cascade too, but it's easier for the compiler to do it with switch. Why? Because you've expressed your intent. You've declaratively said what you intend to do. And if you're good to your optimizer will love you back. So if switch is so great, why not use switch? Well, actually, the question is kind of backwards. Switch is great. We want more switch. It is equivalent to an if cascade if you remember to write those breaks. By the way, writing the breaks before the case is just my personal current style. I hope you adopt it. I hope you can adopt inspect instead soon, because I want to just say up front, there ain't no fall through coming through here. I just find it more convenient because I think break case mentally to me is an atomic unit. But that's my personal style. But only if you write the breaks do you prevent fall through. And we've all seen bugs where you fall through by accident and get wrong results. If only switch weren't limited to just a single int at a time and an int, compile time. And if only it were available elsewhere in the language, because there are other places where I do if-like tests that I would like to switch. So the current proposals for pattern matching in C++, the 2 active proposals both look like this. Inspect, just like switch, but with a different keyword. Again, the expression, and then for each alternative, you write a pattern to be matched, and if that pattern matches, then a fat arrow, and then the structured block of code is actually scoped, no implicit fall through, if that alternative is selected. And you can use this as a statement or as an expression. So sometimes you might want to write cout, chevron, inspect, and then decide what thing to output. So you can use it in an expression too, in both proposals. So unlike switch, it's robust, no implicit fall through. It's general, it doesn't just work with non-integers, it works with predicates that you write yourself. It works with types and with values. It works with an elaboration, a generalization of structured binding decomposition, so you can express nested patterns. And in my proposal, I'm arguing strongly, and I believe that the 1371 authors also agree and are moving in this direction too, that inspect is so good, we should be able to do pattern matching elsewhere, not just inside inspect, but in other places in the language, and that's where I'm going to start. But first, a little frequently asked questions. Why not just use the keyword switch and generalize what you can write inside a switch? That would work, but remember declaring intent? I was one of the ones who said, well, if you just say switch, you can just scan forward and then see the fat arrow and know you're doing an inspect style, a new style switch. And then I realized I just violated my declaration of intent up front. I said, oh, you have to scan the body to see what this is. Better just have a keyword up front, especially in a language that has switch to, which we continue to have for backward compatibility. Why add this fat arrow to designate the alternative? It's mere syntax, this can change, but the current thinking is it's more visible than the colon of the cases, and to connote that it yields this alternative as a result. So that's a quick, why did we pick that syntax? So what I want to get into in the meat of this talk is what if, as we're thinking about pattern matching, what general cleanup in the language could we do that would also make pattern matching easier and better, but would also benefit the rest of the language and make pattern matching easier to make general in the language. So you might have seen is and as in other languages. I know several languages have these kinds of features. So in the proposal that I wrote, so now here I'm talking not as representing the committee, I'm just talking as a single proposal writer about what my personal opinion is on, hey, here's a direction worth exploring. So this is just my personal thinking. I'm not speaking for anybody else. I'm proposing, what if we had is expressions and as expressions in the language? X is C means X, which can be a type or an expression, is, that's a static or a dynamic, is a relationship with C, which can be a type or a value, or a type predicate like a concept, or a value predicate. As is a general cast, and we sometimes distinguish between conversions and coercions, but as I'm casting to another type, is never changes identity. It just queries the object or the type in place. As could create another object. If you say as int, you might convert to a new int and to get an R value, or if you say as int ref, now you're asking to view the existing object as an int ref, so as might or might not create a new object, is never creates a new object. It just queries. And I'm proposing that both of these work for static and dynamic typing. Now, dynamic typing is something that is fairly newer in C++, and we've been doing through libraries like Any, Optional, and Future. Those things will help us to do more dynamic typing things in a way that fits with C++, and therefore I'll show you how is and as are customizable for those types. But to get context, let's see what we're currently doing today. Our type queries, I'm going to distinguish between static and dynamic, and also between the ones the language supports and the ones we do in the standard library for the standard examples. And those are pretty much the same thing, except for, you notice there's one row of overlap where the language actually has one little bit of support for dynamic typing. So all the static stuff is type traits. Oh, we have a glorious number of type traits. Those look like you're invoking a template. Those are intrinsics the compiler writer wrote for you. Those are not libraries. Those are part of the language, even though they look like a library style syntax. Is this the same type? Is this type a base of another type? Those kinds of queries. Then we have the one bit of dynamic typing, other than exception handling cache, but that's related. One bit of dynamic typing available to the user in the language, and that's dynamic cast. And it's entirely for raw pointers and for inheritance relationships using specifically the class and inheritance and a virtual function systems baked into the C++ language. So for language support, that's all you get. Inheritance, the only dynamic typing in C++, the language. But what a powerful library building language we have, and we did, and we have a variant. So now I can have a dynamic type, like a variant of int, comma, long, comma, string, where that same object always has that static type, but at different times in its lifetime, it might hold an int, or a long, or a string, only one at a time. That is dynamic typing, and it means you need a dynamic type query, which we currently spell stood holds alternative. Is this variant currently holding an int, say? Any is like variant, except it's not a bounded set of types. You can really actually set it to any type value. It does it through type erasure. And for it, we have a different incantation. A.type equal type ID of t. That's how we say, or do you currently hold a t? Like A.type equal type ID int. Do you currently hold an int? Then we have optional, which is just barely a dynamic type. It's basically, it always holds a single type, a value of a single type, like int, or nothing, so it's nullable. That is dynamic. If it's not null, there's only one type it can be, but it might or might not be holding a value of that type, and so we say O.dot has value to say, are you currently holding an int? And finally, you may not think of future as a dynamic type, but if you just bought what I said about optional, future can largely be thought of as an async optional. It either holds a value of type t or it doesn't. It just happens to have async semantics where it can be filled, where somebody else can fill the value. You don't have to do it yourself. And there we have this long incantation because if you've been watching, the concurrency TS had future.isReady, and we took that out when we standardized it. So if you want isReady, this is what you write. And yes, GCC and Clang optimize this for you because they know you're writing it as a workaround for the lack of isReady, but that's another talk. That's what you write, to say, do you currently hold a value of type t? So now let's add a third column on the left, which is safe or unsafe, because so far all of these are safe. These are type safe. When it comes to casts, we gave you more stuff. We gave you C-style casts. We gave you reinterpret casts. And if you think those are different, remember that a C-style cast can do a reinterpret cast. It's specified as a series of things. If it can be this, we do that, else this, and the last one is reinterpret. Those are unsafe, so they're red on the slide, and we discourage using them. Constcast also is suspicious because it can it's the only time you would use it is to cast away const. And then we have function style casts of two flavors, parens and squiggles. We have static cast, dynamic cast, and then again we get into the variant any optional future where we have different incantations to cast to a particular type. So if I have a variant and I want to say, hey, let me get an int out of this variant, I would write std_get int v as one way to do it. For any, I would write std_anycast. So this is all part of C++20. We have this today. What I'm proposing is that we spell these all as is for the first column and as the right column, with the exception that I don't think it's important to support the top ones, the unsafe ones. So is and as are always safe. If you want reinterpret cast, it's still there. Nobody is taking away your reinterpret cast. You can still spell it, but by bejeebers, I'm gonna make you spell it so that I can grep your code when the bug comes in. Let's take a look at this, and I want to invite Sean Baxter. I've mentioned the Circle compiler. Please, Sean, come up to the stage. Can you give him a round of applause?
Sure.
So the Circle compiler, here, if you go to Godbolt, you will actually see a drop-down, which we're using here, for of the different compilers you can use. One of them is C++ Circle, so that's the one we're using here. Sean, want to give us a quick rundown of what is the Circle compiler?
Sure. So Circle is a modern C++ compiler, and its distinguishing feature is that it kind of has all the features. So there's reflection, there's user-defined attributes, there's enhanced packs, there's shaders, there's CUDA, and there's a meta context that lets you execute any code at compile time. In addition to that, I've implemented some of the more interesting standard proposals. There's universal template parameters, there's deducing this, and this summer I implemented Herb's is-as pattern matching proposal, which has been a good exercise.
So I said, well, hey, I could use some demos, and so we've been working, so thank you very much for that. Mm-hmm. Sometimes you might have seen Circle on Reddit and places like that over the last couple of years. Some people think it's like, oh, it's a Clang fork. No, it's not. Or it's not C++. It is a C++ compiler that you wrote, a front end on LLVM.
Right, so it's a from-scratch C++ compiler. It targets the Itanium ABI Linux 64-bit, LLVM 12, and it has the usual set of Clang switches for emitting PTEX or emitting bitcode or assembler or whatever you want. So it's not exactly a drop-in replacement for GCC or Clang, but it's pretty close.
So if somebody wants a winter project, build a C++ compiler, I think that just is mind-blowing. So
Yeah.
let's try this C++ compiler with the implementation of this. So here we have a sample set of code where down at the bottom we have some call sites in main where we're going to invoke f with 42, with an unsigned long and so forth. First, let's look at f itself. So f, how many are familiar with the f of auto parameter, what that means? How many are surprised to learn that is a template? That is a template. How many of you are surprised to learn that? A few people. So in C++20, thanks to, as part of the concepts package that Bjarne and others championed through the committee, we now have implicit templates. And this is like generic lambda auto parameters are templates. So tell us what's going on here. This is not C++ code that we can write today, Sean. So what's going on with if auto I is int?
Right, so this is an aspect of the pattern matching proposal. Typically, inside an if statement, you can declare a condition object. That condition object will be assigned to its initializer, and it'll be converted to bool. And if the bool is true, you take the true branch, and if the bool is false, you take the false branch. In this case, though, we have a is constraint. So the initializer x, which is going to be 42 or 501 UL or 7788 or whatever, that x is the initializer, and we're going to subject that to a constraint. We're saying if x is int, which can be known statically, if that's true, then we're taking the true branch and we're binding I to that initializer. So I becomes the value of x, and we're not converting I to bool to test if it's true or false. We're just taking it what it is. And in this case, even if you were to pass the integer 0, the true branch would be taken because 0 is an int, and that 0 is bound to I, and then you can print out that 0. And in this case, we're printing out 42. So it's an alternative style for doing a test in conventional if-else control flow.
So as we uncomment this next line, notice what is stood integral? Stood integral is a concept. This is, so you, among other things, had spare time on your hands and implemented C++20 concepts.
Concepts has some good stuff. Yeah, here we have the concept integral, stood integral, and this just tests if it's one of the built-in integral types. It's pretty equivalent to the corresponding type traits, but x is integral is not a condition object. This is an ordinary expression. You could use it anywhere expressions are permitted. We're just saying if x is an int or a long or a short or whatever, then we're going to take the true branch. So you can use that expression anywhere.
Great. And so for the integer 42, we picked the first one, but the second call 501 unsigned long is not int, but it is integral. So we match the concept. And so what about the next line? Let's see. Now we're doing something that looks more patterny.
Yeah, so the pattern matching proposal sort of completes the picture of structured bindings. So we can disaggregate the initializer x and test its components. So if it has two components and they're both type int, the constraint passes. And since the constraint passes, we're going to declare the condition object, which in this case is structured binding, A and B. So A will be bound to the first component of the x, and B will be bound to the second component of x. And now both those symbols are visible. Again, there's no conversion to bool. The test of whether the if statement is going to be entered is the constraint.
Now, I have a question though, because down here, the second to last line on the screen, I'm passing f of a point, 0, 2, and it's not matching that. Oh, it's because point is long and is a struct that has two longs. What would happen if I turned these to int and int? Would that match too?
Live demo, let's try.
We're about to find out.
Mm-hmm.
We found out already. Yes, there it lights up. See, I hope you're watching the right-hand side of the screen where it's showing the live output. So there, yeah, we can match the two, we view it as a two-tuple. The struct of int, int is a two-tuple. So it's not hardwired, just a tuple or anything. And so let's go back to the point there. And I guess there's only a slight difference with this line. What's going on here?
We're just disaggregating the initializer into 3 components. So it has to have 3 components. If it doesn't have 3 components, then it's essentially like an IfConstExpert statement, and the whole the body of that will not be instantiated, so you don't get these type errors. But if it does have 3 components, they're all integers, then we're going to do a structured binding, disaggregate the initializer x, and print those to the terminal.
Now, you just said something in passing that I want to just dig into a little more. You said as if you had written IfConstExpert. So today, those of you who have been using IfConstExpert, which is new in C++17, you know that you can use it to do compile time stuff where basically IfConstExpert, if that thing is true, that whole branch, or if it's false, that whole branch doesn't exist in that instantiation of the function. So you can do stuff that is actually illegal syntactically for other types. But it's okay, because then that block will be ignored if you don't take the IfConstExpert. You get the same semantics here for the binding without having to write IfConstExpert, but it's the same semantics. So that's kind of powerful.
Right, we can't write IfConstExpert for some of these because you can have a runtime test and a compile time test.
Right.
And it'll do the right thing. If it fails a compile time test, it won't instantiate the body. If it fails a runtime test, it will instantiate the body, but it won't execute it when the program's run.
So if you can still use IfConstExpert with is and as, absolutely. You still need to use IfConstExpert if in the body of the alternative you do something that would be illegal for the other types, because it's only IfConstExpert that really prunes the body. But in this particular case, the only thing we're doing specific to those types is right in the if statement itself, where we're doing the structured binding, and that goes away. That's the part that goes away as IfConstExpert. Now, this next line is perhaps the most interesting line on the slide. There's a lot of going on here.
Right, so we're subjecting the initializer x to an is constraint where we're decomposing into two components again, and we're testing the first one to 0. And this is really just an is 0, and there's a long checklist of comparisons, but it's going to use a quality operator unless there's another overload. And the second component is being tested against even. Now, even is a runtime predicate. It's that bool returning function at line 6. And it uses an invented template parameter, so it's auto, which is like an implicit type name T, and also has the stood integral concept tacked onto it. So this function will only be satisfied if its argument is an integral type. And that's important because we have to protect the function from being instantiated with a double or a string or a pointer or something else that would cause the program to become ill-formed because we're doing a mod operator in the body of that. So in this case, we're passing it a point with a 0 and a 2. And the first component is 0, which matches 0. And the second component is 2, which matches even. And the predicate is satisfied, so we do the structure binding. The second component is bound to y, and the first component is wildcarded, so it's ignored, and we get to print out to the terminal that y equals 2. So I think we can show the importance of using concepts defensively to support more generic kinds of arguments. So if we were to change the point definition from long, let's say, to double, changing some data members, now we're going to set off the error, and we should remove the integral concept on line 6.
Okay, so if I just change long to double, now it makes this point call not match. That just switched to no matching value. But what you're pointing out is that this is why when you write the predicate, you want to concept constrain it, because if I took away that concept constraint.
There we go, and now we have a sort of poorly paginated error, but it will indicate the x mod 2 no longer works because we're instantiating it over double. So the use of the concept makes sure that we can run anything through the if-else cascade and it won't cause the program to become ill-formed.
So concepts for the win, IfConstExpert is still good, concepts constraint, and you'll see more requires clauses. Finally, let's give as a shout out.
Yeah, so as has an implicit is. The implicit is in as is, can this conversion happen? Can we convert the argument x to a string? If we can, we're going to bind that, we're going to perform the conversion, bind it to s, and then print it to the terminal. If we can't, then it'll just go to the next case. So we're passing a pointer to the string literal x, y, z, z, y. We can convert that string literal to a stood string. That'll be bound to x, and the body is executed.
And so just to emphasize, notice that on the right-hand side of that highlighted line, we are just doing string literal plus s plus string literal. That we all know by now that only works if the middle type is stood string. So that's just showing that yes, in fact, we're saying I'm going to declare a variable for the scope of this if branch s. It's going to be initialized from x, but I want it as string. And so the conversion happens. Excellent. Well, thank you very much, Sean.
Thanks.
We'll invite you back up in again in a few minutes. get myself reset here. So just so you have it in the slide handouts as well, here is a screenshot of what we just saw and the Godbolt link you can use to try it out. And you can also use this in other places where is and as, or is can be used in other places that require Boolean conditions. For example, in requires clauses. So you can try this code on your own. Here is essentially the same example, but being expressed to write a set of overloads of function templates that use pattern matching and is to constrain that requires clause as to which ones get selected. And I think this shows the power and the generality that we should be aiming for as we add features to the language. So notice that so far, I have not said the word inspect on any of these demos. This is just is and as in the language, but boy, doesn't it start already to feel pattern matchy. And so it turns out we've already looked at a lot of the pattern matching proposal, at least in 2392, before we've even seen inspect, because we can use it throughout the language. Now, I want to emphasize, though, that this has to be extensible to work well for dynamic types. So here is a screenshot of the relevant section of my paper that talk about operator is and operator as. And the table basically shows, hey, here's all the ways that we spell is and as today for any, optional, variant, and so on. Here is what gets invoked as we wrap them, and I'll show you the code next, for each of those types and to supply operator is and operator as. And two things I want to highlight here. As we wrap, yes, you can just say is int, is long, like do single type queries or single predicate queries. But we want to optimize this. So similar to the way switch optimizes repeated results in a row and does a calculation once and then does a jump table instead of a series of tests. Similarly in spirit, for variant-like types and any-like types, there are optimizations where you could write operator is so that the compiler only, if it sees a list of inspects, is int, is long, and so forth, it only queries the type once, in this case a variant, to get its index of the active type, and then uses that to say, oh, is that the index of int, is that the index of long? So you're not doing repeated type queries. The similar optimization as we have for switch jump tables exists. And this is common to both proposals. You'd want this in any pattern matching implementation. And you get a similar thing for any, instead of an index that goes through type info. But I cannot stress enough, the end result of this is that you get to write code like the bottom left. And you might be tempted to think that here's Herbie going at it again, looking for syntactic sugar and simple code because he can't handle the truth of complex code. It's like, we all like simple code. As simple as possible, but no simpler. My point here isn't that this is better because it's simpler, although it is. That it's simpler because it's more regular, although it is. My major point here is that I can write that in a template and it will work for optional, any, variant, future, cute variant, LLVM variant, LLVM any, boost any. Just if I write the operator is and the operator as once for each of those types, then it hooks in. And that's really important. And just, I want to make a subtle, nuanced point here about that. Let me make sure it's sufficiently understated. Yeah, I think that's subtle enough. Whenever you design a language feature or a library, which applies to all of us, and you decide to pick a spelling for an API, for a function that is different from what another similar type uses, you have just prevented people from using those two types in a single template. Syntax matters for generic code. Generic code wants things to be spelled the same, because unless you want people to go and write an IfConstExpert cascade, oh, IfConstExpert, they provided this function, or IfConstExpert, nobody will do that. And plus that'll be closed-ended, it won't work with your new type. Consistency in spellings, not when they're different semantics, but when they are the same semantics, consistency in spellings enables generic code. This is the same reason why Bjarne in D&E wanted UFCS, Unified Function Call Syntax, that we still don't have in C++20, and it's why we still want it. Because there are quite a few functions that you might choose, operators, but also any regular function, you might decide to make a member or a non-member function. And that's cool as a design choice. But now step back to the user of the function in generic code. Because the member function call syntax and the non-member function call syntax are different syntaxes, they don't know which one to use. If they pick the member function one call, they'll only work with types that supply it as a member function. If they supply it as a non-member, if you supply it as a non-member and they call it that way, they'll work with your type, but only others that supply it as non-members. Now, we actually do have the tiniest bit of unified function call syntax in C++. We've had it forever. It's for operators. Because if I write A plus B, that will invoke a member or non-member operator plus. We want more of that because we want generic code. This is why I view it as critical in my is-as proposal that there be operator is and operator as, so that we can bring the dynamic types into a unified syntax. So here is the actual code that I'm proposing for std optional. You'll see this code compiling live in just a moment. So operator is for std optional of t, returns a bool, and whether the optional currently holds a t, that's the same as does it have a value. So it just returns x.hasValue, that's it. And operator as, now I want to convert this optional of t to a t. Can I do that? Yes, if there's a value. I just call .value and I return autorefref. You see the paper for details, but basically that's just following exactly the design choice we already have for .value for std optional, which sometimes returns by L-value reference, sometimes by R-value reference. You get exactly the same semantics for optional .value when you invoke it using as. And I think that's important. There's a Godbolt link you can try for that as well, for all of these. Here's the same thing for std variant. Blink and you'll miss it. You'll notice that the boilerplate is pretty much the same, just is happens to call .index because we get that indexed optimization. And as calls std get of I, which is the way that you get the ith member of a variant if it's the active one. Now notice that blue line. Sean pointed out to me why that blue line is so important. In a nutshell, that is how, that requires, which is a concepts requires clause, but for just constraining the integer I, that is how the compiler implementing as knows how many types there are. So that's one question that came up in evolution working group. How does the compiler know? The blue box is how the compiler knows how many types there are, because it spinays away in the right places, or gets non-selected in the right places. Finally, for std any, we have operator is that calls .type, and we have two operator as's, and the reason for that is simply because there are two forms of Anycast. There's the form that says, give me a copy of the value you're holding. If you're holding a t, give me a copy of the t. And there's a one that says, give me a reference to the t you're holding. The way you incant those is different today. For the second one, you have to write the bottom green box, std Anycast remove reference t star address of x. Then you get a pointer to the object. So you have to use that form and know how to use it. Because we've wrapped that inside as, when you use it any through as, you just say as t or as tref, and it does the same thing. But the syntax is more uniform. So let's see the demo. John, can you come up one more time? And let's actually see this happening in real time. So here is Godbolt reloading something different than I saved. So let me go fix that. What we want to do here is go to that Godbolt link. There, now we're in the right place. So let me just scroll up for a bit and show you that above here is all the code you just saw. So we go way up, there's our type traits, any optional variant includes. Here is the is and as operators for std any that we just saw. the is and as operators for stood optional, exactly what was just on the screen, and is as operators for stood variant, which was exactly what was just on the screen, so I won't talk through those again. But now what we're doing is writing a generic function. And so tell us, Sean, about this generic function f.
All right, so f, again, has an invented template parameter, so you can imagine substituting auto with a type named t. So it's going to take an L value reference to its argument. The first thing we're going to pass is a pointer to a string, x, y, z, z, y, and that's a built-in type, and we know it's not an integer, so we're going to print out no match to the terminal. And we're going to do the same thing. We're going to print pass 1 to f. Now that deduced type is int, and that int is an int, so that's true, and we're going to print into the terminal.
Okay, so those are static types. And we've been able to do that since forever without is. But notice that we're doing, by the way, just a subtle detail, you'll notice this happens to be using the expression form of inspect, because this entire inspect expression is inside the middle of a cout expression, a cout statement, which is kind of useful. But notice that for all of these demos that we're about to do, all of these queries, we're just calling this same is int. Is it an int or is it not? And then if it's an int, you can do all the other things that we just showed you. So this is static typing so far. Let's do some dynamic typing. So what about any? If I start to uncomment this, what have I got?
So we're initializing any with a pointer to a string, and we're passing that to f. So the invented template parameter is deduced as type any. It's not deduced as type pointer to string. It's not deduced as type int. So we're going to use is int to try to extract the dynamic type inside. And rehearsal yesterday, I was blanking and becoming flustered because I forgot what the implementation for the member function for any to extract the inner type, or the member function for optional or variant. And that's the point, which is you don't have to remember because these are uniformly named. You can use is to test and as to extract or to coerce. So
on line, I think that's 52. This third line from the top where it says is int, that's simply saying whatever x is, which in this case is stood any, is int. Oh, well, what is the type of x? It's stood any. Is there an operator is for that? There is. We'll invoke that operator is and give you back the result.
Right, and this does like full ADL lookup. So it can find non-member functions, which is important here because this is using lib standard C++ 10. The any and the variant and the optional haven't been edited in any way to support pattern matching. So we had to externally define these. Now, in the future, if this becomes standardized, you'd add these as member functions or as friend functions. So it's using name lookup and finding the user-defined overloads through that extension point, and it's using the any member functions.
Yeah, and thank you for mentioning that. I forgot to mention when I was talking about when you add the operator is and as customizations, that's not invasive. This demo is the unchanged shipping production of any variant and optional types in Clang, in libc++. So you don't have to go modify types. Of course, if we standardize it, then the types would want to opt into that. But what if now if I take that same object and I give it the value 2 and I invoke f?
So now we're going to see int is printed to the terminal because the user-defined implementation of is int is finding an integer contained in the any. It's using RTTI, it's using type ID, and the compiler internals are delivering, yes, we have an integer in the affirmative.
So the first example was static typing. Now we've done dynamic typing with any. Let's do dynamic typing with optional. So the same thing here. What's going on here?
Right, we see 2 more lines. We're going to see a no match and an is int. So optional is the type of the invented template parameter t, and it's doing name lookup, and it's finding above all this code, it's finding the extension point where we did a user-defined operator is, and it's calling operator is, and that's coming back true for the integer 3, and it's coming back false for an uninitialized or a null holding, a nothing value of optional.
And then finally, variant.
Variant's a more complicated case, but it looks the exact same in the user code. So the compiler is actually polling, it keeps hitting the variant with an ascending sequence of integers, saying what's your first 0th alternative, your first alternative, your second alternative, until that requires clause on the operator is false, and that breaks this this polling. And so that's the way the compiler can interrogate what the variant holds. And it's also going to find the active variant member, which in this case is going to be a character pointer, which doesn't match the isInt query. And in the second case is going to be an integer, which does match. So it's a different form of dynamic interrogation of types.
So for the variant case, they call it variant.index once, gets the active index, and then instead arranges to instantiate the operator is template with that index, and then get the right answer for it. So thank you very much, Sean. Take a break, but we'll call you back up one more time in a few minutes.
I'm getting my steps in today.
Okay. So here is that same for the handout. So if you get the handouts afterwards, you can see the same example, and you can godbolt it yourself and see how, and try it for yourself and try variations. So now that we haven't talked about pattern matching for all this time, although we sort of sneakily have, we've been talking about pattern matching everywhere but the inspect statement to have something general in the language. So now that we have it, let's put it into the inspect statement too. By the way, if that sounds backwards, it's not. Several other major languages, including specifically C# I know of, took the exact same path. So when I talked to the C# designers about this, and the current lead designer, Mads Torgersen, he said, yeah, you know, we found the same thing, because for us, we had is and as, but we didn't have is as extensible as you're proposing for C++, because to this day, C# is cannot call user code. It's purely a compiler intrinsic, it's not extensible. But because we've always had is since way back, and we've always had switch, when we added pattern matching later, it was very natural because we already had is, we already had switch, so we just merged them together. It was pretty incremental. We added a major feature in a pretty incremental way because we had the building blocks. Let's do that here. Here is the summary pasted directly from the paper. And at the bottom, you'll see that each alternative in the inspect expression optionally introduces names, so introduce names come first before is, as, or if, but then it can be followed with possibly a chain of is constraint, as, type, or extractor. Or you can even write a general if, because sometimes you just want to write a custom thing occasionally as well, and you can do that too. But is, as, if are your alternatives. So here's a quick starter example. The top is the switch we would write today, and this is one of the reasons why people love fall through. They say, hey, isn't fall through wonderful? Case 1, case 2, case 10. If it's any of those, return X. Yeah, that's great, but you don't need fall through to get that. You know, we do know what logical OR is. We have that technology. So we can simply, in the inspect statement, and you can try this out on the circle prototype, you can say is 1, or is 2, or is 10, or something general, call a general predicate. Is it a perfect square? Then return X. So you don't need fall through to get that benefit, and that's a starter example of what an inspect looks like. So OR is one of those conveniences you can use, but let's go through the 3 conveniences. And is the obvious thing for multiple constraints. Is shape and is visible, say. Or is when you find yourself writing multiple patterns that all have the same result. Well, you could just repeat the result, or you could just write OR and write the result once. And don't repeat yourself. The DRY principle, I prefer the right-hand side. And I'm also speculating, and this is jettisonable, but I have found it useful while I was writing the examples in the paper, and like half the paper is examples. So I have found it useful, and I hope that we get something like it. When you write multiple patterns that have overlapping constraints, so the sub-constraints are common, instead of repeating them over and over again and maybe writing a typo and getting it wrong, again, don't repeat yourself. You can extract those out, so instead of is shape and is red, is shape and is above Y, you can just say is shape, brace. If it's a shape, now try all these alternatives, and they're as if anded. And that if none of them match, then we just go back out and try the next thing below the is shape, and that's fine. But this is the left-hand and right-hand side are equivalent here, It's just an easier way to write them and not repeat yourself. And this part is available only in inspect. So Sean, one more time, please, get in your steps. And let's see if we still have. Yes, we do. So walk us through what's going on in this example, which is very similar to the one that we already saw, but we've now grouped some common things. Like what about this first grouping here on line 10 is integral?
Right, so this allows us to nest these clauses, these inspect clauses, in a way that's, I think, more natural and more prone to executing your intent than nested if-else statements. So first thing we're doing is we're saying, is the argument x an integral type? This is a static evaluation, and that body will only be injected if x is in fact integral, and that prevents a lot of these substitution failures from causing your program to be ill-formed. So we're saying if x is integral, then attempt to compare x to an integer. If it is an integer, then print that out, and we have a backstop case, is underscore, which matches anything. So that is our if true case.
And so if none of those match, then we drop through to the next case. What's going on here?
So now we have a structured binding, and there's an implicit constraint in all of these structured bindings. The implicit constraint is that it can be decomposed into two elements.
So this is as if I had written this, right? It's just implicit because it can't be the structured binding unless I had done that, right?
Exactly. Yeah. So it's better not to write more stuff than it can only be bad to write stuff you don't need to write. So we have this decomposition into A and B, and that binds these declarations to those members. And now we have entered the group in there, and we're testing if the decomposed members are both integers, and we're printing those out. And then that's a compile time test. And then we have runtime test, which is going to test if A is 0, and we're going to evaluate even and pass it B and test if B is even.
Great, and the rest are as before. So this is your last time up here right now. Okay. Let me just say thank you again for taking the initiative to implement this and a bunch of other proposals from the Standards Committee just by reading the mailings and writing them in a compiler. That's pretty impressive, and thank you. It really has helped because as Sean has done this, he found several bugs in my proposal. So because you learn stuff when you actually try to run the code and it's not just in Word, right? So in particular, when we were talking about is even needing integral auto X, that it wants to be constrained, that came through the implementation and actually trying to use it. So the next version of my paper will say integral. My original code did not say integral there. So thank you for that, all the work and the bug fixes. We appreciate it a lot.
You.
So again, for the handouts, if you have that you can download, and so you remember what the Godbolt links are. Here is the screenshot and the Godbolt link. You can try out yourself. And the main point I want to make here is we just saw this code on screen, although you notice I've indented it a little bit more. The reason I indented it a little bit more is because now I'm going to go back and show you a slide we saw earlier. And I'm going to go back to the one I just showed you. Then I'm going to show you the slide we saw earlier. And I'm going to go back to the one I just showed you. Inspect, if. Inspect, if. Are you getting the point? These aren't just two things. These are one thing, and we're calling it pattern matching throughout the language. So this is something I think is exciting, and regardless of if we use this exact syntax that I'm proposing currently, let's do whatever we do, let's keep it regular and consistent, because this is easier for me as a trainer to teach and learn. It's easier for me as a user to teach and learn, because I learn one thing, not n things. And that's sort of been a theme of this talk. Now, there are some refinements in progress. So for example, if you look at the previous proposal that's also still active, 1371, instead of is, it would use case here that only worked inside these patterns. And it would use star question mark for dereferencing, whereas I'm using star for dereferencing. So those are details. But the main thing I want to point out is that in my proposal as it was currently published, you had to put all the introduced names up front, then is or as, and then the constraints, which would always refer to existing names. Therefore, there was never any ambiguity about, am I introducing a new name or not? So if you see a name, you don't have to worry, am I shadowing some variable? Did I just introduce something, or am I referring to that variable in scope? If it's to the left of is, you're introducing it. If it's on the right of is, you're using an existing name. And I kept them totally separate, and the feedback I got from the 1371 proposers, from Sean, and from others was, you know, that nice principle of separating them, that works even if you do it distributively in each section of the pattern. And so at the bottom, the next revision of my paper will also allow the doing that in each position of a decomposition pattern, and then there's no duplication of the pattern, whereas in the middle currently you would have to duplicate the pattern structure. Using that syntax, here is one of the most complex examples in the paper. It's actually on Wikipedia's pattern matching page. This is a very common example of balancing a red-black tree. So every node has a color, a left-hand pointer, a value, and a right-hand pointer. And as you insert nodes into a red-black tree, which is basically what StudMap and such are built on, you may need to do rotations of the tree. You don't just put another node in the binary tree, you may insert it and then do a rotation to keep the tree roughly balanced. And this is a well-known algorithm. And what we're doing here is we're ORing together 4 alternatives. The first one, and they're all if I'm the black node, so I could have extracted that. But if this is a black node and my left child is red and its left child is red, that's the first alternative. Second one, if I'm a black node and my left child is red and its right child is red, and then similarly for my right left and my right child is red. In each of those, notice I'm introducing the same names, A, B, C, D, X, Y, Z, in different positions, but with the same types so A is the same type in each of these, but in a different position. I'm saying, okay, if you're in this case, these are the ones you want to grab to move to this configuration. But if you're in this case, these are the ones you want to grab, but we always do the same thing. We have the same result, we make the same configuration, and that single result is the rebalancing. And the 4 alternatives are just the 4 cases for how you might want to map the rebalancing. So this is an example of how powerful pattern matching can be. And of course, there's the is catch-all case, is wildcard. If none of those happen, then we don't need to rebalance and we just return this. So we've talked about why do we have switch, and then why do we want more switch with inspect. I've tried to show why I think it's important to think more generally, not just about how do I add inspect to the language, but how do I add pattern matching to the language. Inspect is just one place I can use pattern matching, I hope. Then how we can do inspect itself. I probably should have renamed that third section inspect using is and as, because both of the middle sections are about pattern matching using is and as. But now let's just look forward for a moment. Earlier in the talk, I mentioned that C++ is historic. C++20 is historic, and it really is. Are we done just because we're largely D&E-complete? I mean, that's a great milestone, and we should celebrate it. And it does not mean we're done in either sense of the word, nor does it mean we're finished in either sense of the word. English is full of this pun. We want to do things like static reflection, contracts, pattern matching. But I've been doing C++ so long that I kind of feel married to it, like work marriage, you know what I mean? And in a good way, it's a happy marriage. I'm in it for the long haul. I plan to be here for many years yet. I'm having a good time. One of the things to keep a marriage happy is you overlook unimportant things. Like people come up with 100 laundry list things of C++ they don't like. Most of them aren't important. Our spouse may come up, or any long-term relationship partner that we have, may have little foibles, and they're not important, so we overlook them. They're not important. But when there are issues, a happy marriage continues if we can talk about them and work them out. Can we do that? There are 2 in C++. And we know what they are because we hear them all the time. And initially, I'm going to phrase them the way that we normally hear them because it's important to listen. So this is what our users are telling us. The words they're using are C++ is too unsafe. They are saying C++ is too complex. They have not been saying this for a few months or a few years. They have been saying this for 30 plus years, and we have kept improving C++. We absolutely have. I love this language more than ever. It is simpler, safer than it has ever been, but these complaints have not stopped. Evolution, as usual, has not solved these problems, at least not yet. So we have to acknowledge that. It has started to, this pressure to address these has started to affect the Standards Committee. In the last 3 years, we have had at least 2 serious proposals to take breaking changes in the language to have incompatible regions with language dialects or flavors or additions. One of them suggested doing that on module boundaries. So code you write in a module can say, oh, in my module, I'm going to use an updated syntax for C++ that maybe cleans some stuff up that we all know about and we've been wanting to clean up for a long time. Maybe there's just never any narrowing conversions at all, ever. Maybe ADL works the way we want it to, but but it does mean that in this module, the same code could mean something else than C++ code in another module. That kind of breaking change is not cheap, and it should not be looked at lightly. Just look again at Bjarne's keynote yesterday, where from the very first slide almost to almost the very last slide, he emphasized the importance of compatibility with C, with older C++ as we evolve. That is non-negotiable, it is vital, but then how do we do cleanup? So one of the proposals was to do such breaking change cleanup on a module boundary. And I think that can be done without having the problems of Python 2.3, because we all know Python 2.3, that was not, in retrospect, a good way to manage that. And even the people who managed that have told me personally they would not do it that way again. They just didn't realize the costs of breaking compatibility in that way. And they would not do it that way again. And so we all learn, and that's fine. So I think we could do that otherwise. But the other proposal is also proposing not on module boundaries, but on Rust-like additions, so epochs, I think it was called in that proposal. One concern I have is of the plural of that, because if we have epochs, that may be fine in a language with a relatively small number of users, about 1% of C++'s users, but with billions and billions of lines of code, and 5 or 7, these days I'm more hearing 7 million users. Nobody can count accurately, but it's a lot of C++ users. That's hard. And yet we are seeing serious people come to standards meetings with proposals to take breaking changes in standard C++ for these reasons. So having beaten that drum, just so we take it seriously and acknowledge there is this pressure, can I rephrase these a little bit? Because the way they're phrased, this is how people say it to us. And I think it's important to listen. But I think it also leads us to not always the right solutions that we're looking for. For example, too unsafe, I think that's actually literally true. But phrased that way, it makes it sound like, and therefore we should have something that is provably type and memory safe, which if you look at Bjarne's second talk yesterday, I think is over-indexing. And let me rephrase this, and maybe that will explain why. Instead of too unsafe, I would phrase it this way. It is too easy to silently write bugs, and many of them are type safety bugs, things the type system could have checked but didn't for whatever reason. Now, we saw some examples in this talk. We saw a C-style cast, because guess what? It does a cascade of things. It's a mystery cast. You're not sure which of these 5 things it's gonna do. And by the way, the last one is a bejeebers, it's the Reinterpret cast. It might hit that. Roll the dice and try your luck, sir. That's what C-style cast is and why we shouldn't use it. Static cast to a derived pointer from a base pointer, static downcast. Still seen in production code worldwide in major projects I know most of you used this morning, such as Chromium, because, well, we do other things to make sure we get the types right. I got interested in this because I saw the CVEs, the reported vulnerability reports, come back where the root cause was those static downcasts. Were they doing the static downcast to avoid the cost of dynamic cast because they knew the type was right, and we were looking at it as a CVE because it wasn't. They got it wrong. And we'll all get things wrong. That's not dissing anybody. It's just We want to use the safe tools in the language, but this is an example of where in C++, yes, it's too easy to silently write bugs. But if we phrase it this way, that lets us see that, sure, full type of memory safety is one answer. That would address this. But can we do it with the zero overhead principle? Don't know. Somebody should keep trying that. If I phrase it the lower way, too easy to silently write bugs. Okay, now I have more tools. I don't just have the hammer and everything that looks like a safety nail. I have more tools. If right now, the safety-related bugs, the frequency with which we silently write bugs that end up in vulnerability reports and exploits and on Hacker News and in the New York Times, if that was 100 times lower, we wouldn't be having this conversation. Nobody would care that C++ is not formally type or memory safe. We are having this conversation because it's so common, not because it's non-zero. If it were 100 times less, we wouldn't be here talking about it. It would be fine. So what can we do to drive that down further? Too complex. I would also rephrase this one, and this one's actually closer, but I would be a little more precise. I would say it's too irregular with too many special cases and interactions. There's more stuff to learn, and not always consistent. So you have to do the rote learning instead of pattern learning. And so much of it is because I can't directly express my intent. I can't say what I mean. What I want. I have to say how to do it, not what I want to do. And we saw that again today. If I want to get the T that this dynamic type is holding, well, if it's a variant today, I write stood holds alternative. If it's an any, I say a.type and compare it to type ID of T. If it's an optional, I say dot has value. And you gotta teach this stuff. And it kills generic code, because what's bad for people is bad for templates too. So we've seen examples of both of these. But I think I hope that I've also been hammering from the very beginning that we have the tools for solutions. And so if you take away nothing else from this talk, but this last slide, this is the slide I hope that you remember, that maybe you'll talk about later in the conference as we're all here together. If we choose, and this is a choice, if we choose to intentionally evolve C++ toward abstractions that let programmers directly express what they want to do, their intent, in a regular way, so not with divergent syntax, and actually cleaning up existing divergent syntax where we can, then more often than not, several things will automatically happen, just organically. Will naturally improve generic code. It'll just be naturally easier to use our type in templates because we've reduced divergent syntax and semantics. Will naturally improve simplicity for users because there's less to teach and learn, the fewer special cases. What's good for generic code is good for human beings too. And will also improve safety, because did you notice that when I'm proposing we introduce is and as, that we're not supporting the unsafe as cases? I'm not interested in supporting those. So if you're using as, you know that the code is type safe. You can still use Reinterpret. It's there if you want it, but we're giving people tools that are safe, that are regular, that let them express their intent. And we can do that as we evolve C++. So if we do that, I think that we'll make great inroads on two chronic problems that we have to acknowledge. And it's not just about the tools vendors have been working hard enough. It's not just that C++ programmers are lazy and haven't been reading the right books and doing what they should do. If it were those things, we would have solved this by now. But the fact that we're hearing those same two things for 30 years tells us, hey, there's something that we should attach. And I think that this is something we can do differently and better that would help those things. By the way, we have examples. Let me fill in the middle of the slide. For example, unified function call syntax is an as that we talked about here. Last year, I talked about parameter passing where you say, and it's an in, out, move, forward, or out parameter, and showed how the code is simpler, how we're declaring intent. It's just as optimal, and it enables other safety. And I want to focus and brag a little bit about the first one on that list. All of these features I just listed in that example list may sound familiar because I've given talks about them over the last 6 years. So about 6 years ago, and I've said this before, about 6 years ago, I sat down and looked at C++ all up, but I spent about a year going through saying, how could we look holistically at all of C++ in order to make it simpler and safer? How, could we refactor it? What are common things? What are the good things? What are the irregular things? How can we address this? How can we understand the Gestalt and Weltschmerz of all of these things and all of those things that go together? And all of the talks I have given in the last 6 years, including this one, have come from that work. They may be on apparently different topics, like parameter passing. What does that have to do with pattern matching? Nothing, except they're both on the theme of generality and of expressing intent in a regular and safe way as we evolve C++. So of all of these things, the first significant one to enter the standard is the spaceship operator. And I'm going to brag on this a little bit because, yes, as with most standard features, we cleaned some things up after we shipped the standard. But I think it's been a resounding success story. And I may be biased, it's my feature. But the spaceship operator is a fact. It is not an opinion. It is a fact because I counted. I know that it did this, and I don't know of any other standard C++ feature we have ever added that has done this. When we added spaceship to C++20, it is the first time I know of that we have ever added a feature to standard C++ that made the standard smaller. It made it about a dozen pages smaller. And you say, well, wait a minute, but you added stuff. Yeah, we added stuff. We added about 10 pages, something like that, 8, 10 pages to the core language specification to say what spaceship should do. But we then also applied it throughout the entire standard library and saved double the pages in the standard library. And that was a net reduction in the size of the standard. I think that is evidence that it is possible to make C++ simpler to teach, learn, specify, use in a way that makes it better, even on an incremental evolutionary path. And I hope that as we continue working, and these are all long-term features that will take years, and not all of them may make it, but I hope we get unified function call syntax. I hope we get something like is and as, and we will get a better and safer C++. So let me leave you with that thought. Looking forward, abstractions that let programmers directly express intent and are regular, not divergent in their spellings and semantics, I think is a key to an emphasis for C++ evolution that will take us way beyond another 30 years. So thank you for listening to my nattering on. We have time left for questions if you want to come up to the microphones here and here.
Thanks for the great talk, Herb. I have a very simple and specific question. The alternatives inside the inspect statement, am I able to expand the parameter pack over those?
You should be able to. Sean, does your implementation currently do that?
No, I don't think so. It didn't cross my mind. I mean, email Herb or email me, and I can try putting it in and see what happens. I guess that's, it's not part of his proposal necessarily, but I will put it in and see what happens.
That's a great suggestion because the proposal should say what happens, because one of the things about a standards proposal is you don't just say, here's my nifty little feature. That way lies madness. Definitely you should be looking at the whole language. That's the ideal. And you've just seen Bjarne yesterday and me strive for that ideal. But even if you don't get the ideal, the minimum you got to do is say how it works with the rest of the language, what it means when you use it with a parameter pack, and like, can you expand it, and if so, what does it mean? So I need to add that to my paper too.
So I do remember though, you can expand parameter packs inside the patterns. So you can say like is square brackets, and then if you have a template parameter pack, you can expand that, and that'll test each member of the disaggregated type against that. So there is some support, but it's not comprehensive.
I was pretty sure you had done it because you had written 2 pages about pattern matching in your GitHub repo that you sent me of notes, and those pages included fold expressions. So, yeah.
Yeah, there's more in the compiler than I remember.
That was so 2 months ago.
Yeah.
You've actually been implementing support for Windows extensions and support for CUDA in the meantime, because I don't know how he does it. Next question, let's go over here, please.
Thanks. So I would really like to live in the future that you presented. So I want to understand what's standing in our way. So could you please comment on like the kinds of obstacles, such as if there's anybody who thinks that we should not ever do this, and like what are their arguments? Things like significant compatibility conflicts, or even just anything about this proposal, about your proposal that makes you go like, ooh, anything on that theme.
Oh, there's a lot. So the thing, one thing about my proposal that made me go, was fully having to repeat deep patterns. And I had convinced myself that, well, it doesn't happen that often. It only affects 15% of the examples in the paper. But I've been convinced I was wrong. And I was right to worry. That I was right to worry about it and was wrong to minimize it. And I think we have a solution now that actually follows the other proposal. As some of your other questions, what stands in the way of having clean, regular language? It's this hard engineering. Nobody knows if it's possible. And I don't think it's so much that anyone's standing in the way as it's a really hard problem that takes, look at when Bjarne was at Bell Labs. C++ didn't exist. When it was a gleam in his brain, hadn't reached his eye yet, it took, sorry to put you on the spot, Bjarne, it took a world-class super genius years to solve that problem. And we're all benefiting from it now. Nobody stood in his way. They enabled him, fortunately, but it required, the default is nothing happens unless somebody comes along with a solution to a hard problem. The same with any hard problem we've tackled in human history. So I don't actually see any obstruction specifically. Sure, in the committee, people tend to be suspicious of proposals and tend to want narrow solutions. But in some ways, that's because those proposals are easier to write. That's why we see more of them. It's harder to write broad proposals. Now, having said that, another reasonable reason that all the things I've been talking about for the last 6 years, except Spaceship, which is now in, are still underway, and that takes a long time, is because new things require more proof and validation. So before I can seriously bring this to the committee, I've brought it in, I've done an initial presentation. Now I'll go do more presentations in the new year after we've got the C++23 crush out of the way at the end of the year. But one of the things I have to come back with for this, for static exceptions, for meta classes, is an implementation. Show it can be done. And then we can talk more. Then let's see how users use it. What are the pitfalls? I mean, just by Sean implementing this, I found bugs in my proposal. So proposals that do the things I just said. So let me give you the short answer. This is ideal, and it's easier to say than to do. It is really risky to do proposals like this because because they are so wide-ranging and deep, and there's a lot of ground to cover and risks that you need to quantify and address. So, excellent question. Yeah, it's been on my mind. So,
Thanks.
Andre, good to see you in person.
Hi, Sean. We've never met. Congratulations. Great talk. Thank you very much. That being said, I have to share a couple of misgivings I have with regard to inspect. I see inspect and I'm thinking try catch. So one problem with try catch is it's very syntactically heavy. And I foresee that by the time I'm writing like 2 nested inspects, I'm already in a fall mood. And by the third, I want to shoot myself. So it's kind of, it's kind of a bad, I don't feel it's going to scale well with complexity.
So let me ask a counter question. So that's good feedback. What would you write instead? An if cascade? And wouldn't that be longer?
That segues into my next misgiving. The issue here is that inspect espouses, fosters writing completely different implementation for different patterns. Whereas in experience with writing generic code, it's actually slightly different implementations for different patterns. So with inspect, it's like, oh, it's this, you're gonna do brrp. Oh, it's this, something slightly different. Oh, you do brrp. It's completely different disjoint pieces of code. So by the time you have more complex piece of functionality to add, you're going to have inspect or to Wazoo either in sequence or nested, and I don't see that scaling well. I would very much prefer something much more lightweight, and that goes to my pet peeve, like my perennial pet peeve with, I assume each of these snippets in inspect is going to introduce its own scope. Is that correct?
Yes.
So that means you don't get to define things in there that you get to reuse later in a unified fashion. For example, maybe you have a string or a car star and you want to create a temporary string for the car star, but you just want to keep the string as is otherwise. And that is kind of difficult to do with inspect and or IfConstExpert. So what's your take on this?
So first of all, the thing you're leaving unsaid, which I also totally agree with, is that inspect is not an all-singing, all-dancing cure for everything you might want to express. In particular, you want reflection and code generation, absolutely, also. And that's appropriate for the kinds of things that you just talked about at the end. For the nested inspects, and is it a rat's nest, and how usable is it? I'll say only this, that is good feedback. It is exactly something we need to learn as we work with the prototype. And I encourage you to say, do you have the same questions about pattern matching that already exists in other languages, such as C# and Swift? Because so far, their experience has been that users love it.
But they don't do the same things that C++ does.
That's true. So we'll have to learn from actually using it. That's a valid point.
Thank you.
Yeah. Thanks, Andre.
Hi, Herb. We're going to take an online question.
Oh, excellent. I hear a voice, a disembodied voice.
Would quote as automatically resolve as T to as const T ref or as T ref when you're using something like variant?
So if you look at the proposal, off the top of my head, I believe the answer is yes. So if you look at the proposal, and I gave the summary on the slide, but the details are in the proposal, the code that you just saw that wraps it uses an auto-ref return type to forward back exactly the type that you would get back today if you called the existing API directly. That's why I went with the auto-ref for those ones. So it should have the same effect as you have today. Good question. Was there another online question, or should we go to the mic?
Hi. So there was one point during the talk when I was slightly confused, and I was hoping for some help why I was confused. So when we have something as isInt and we inspect the type of a variable, so we inspect the type of the variable. But if we have an optional, it seems to be we are inspecting the type of the wrapped value rather than the optional itself. And in my head, it's a bit ambiguous because I feel like it is both is a legitimate question, the type of the optional itself and the type of the wrapped value.
Yes, that's a very good question. So first of all, do you have the same question about variant? Because optional is different.
Yes.
Okay, because for variant, the answer is easy. So the variant is just a dynamic type that has that currently contains one of a statically known set of values, but it's a dynamic property, whether its dynamic type is int or string. That is what is querying. So think of is as a request for a dynamic type query. If you think of it that way, then variant, I hope, makes sense. Now let's talk about optional. Optional is a confused design for a good reason. It's a confused design because sometimes it acts like a variant of T, null opt, and sometimes it behaves like a pointer. You can use it both ways, including with inspect. I didn't show that because I didn't want to confuse people, but because optional happens to have a dereference operator, oh my goodness, it's pretending to be a pointer, you can use it with the dereference, the star decomposition pattern also. But the reason I chose to present operator is the way it is here, and again, we can make a different choice in standardization, but the reason I went with that is because I still view the main semantics of optional is a dynamic type. It's a T or null opt. It's T or nothing. But yes, you can also use the star decomposition pattern on optional. There is an example in the paper. I almost had one on the slide, but I cut it for time. But you will find an example in the paper. Look for Villez, V-I-L-L-E'(S) example, where you get like a nested tuple of optional pointer to like it's like 4 pointers deep. And you'll see optional be used that way there.
So just to reiterate, so does that mean that if I want to know the static type of something, I bet it is better to use the existing features like isSym and type traits and so on rather than the...
I don't think so. The reason is because, well, I mean, you can if you want, they're still there. But for the static types, is just uses those. It does exactly the same thing. So by spelling it deliberately differently than is, doesn't change any semantics. Is just gives you a regular way to that also extends to dynamically typed things, which currently has sort of a hodgepodge of different APIs that are sort of custom designed for each type.
Thank you.
I find myself a little concerned that as will provide a new way of hiding potentially expensive or lossy conversions that I'm going to have to teach. And so I'm curious, at the very least, how does as handle narrowing conversions?
As does not do narrowing.
Okay.
Now, having said that, sorry. As would enable us to get rid of implicit narrowing because it is an explicit syntax. So the way I view it is as is an explicit syntax. So if I wanted to say, as part of some other proposal, ban implicit narrowing everywhere in the language, as gives me more credibility to do that because I can say as if I want something narrower. Now it may be that you might want to have an additional spelling for like have an as and a lossy as. I'm trying to avoid that complexity. It's possible we might want something like that. But I'm quite happy at this point with as being explicit.
So
because we're explicitly asking for a conversion.
It does allow narrowing, right?
Yes, but remember the problem with narrowing, at least as far as I know, the problem with narrowing hasn't been the narrowing can happen. It's that it's implicit. Oh my goodness, the silent promotions and conversions that we get for implicit narrowing and the bug farms those have caused. It's why we banned it for brace initialization. So today in C++, if you use brace initialization, you can do narrow. No, you can't. Sorry, you cannot. You can't do narrowing unless you also cast. As is a cast.
As is, okay. So, I mean, I've been, spent the last several years trying to convince people to actually enable conversion warnings in their compilers.
Yes.
And so I'm like, if people still enable -w conversion, is an as with the narrowing going to give us a warning today, or is it the same as a static cast where it would not?
An as is an explicit syntax. So sorry that I gave a not well-worded answer. Let me try to word it well again. Implicit conversions are evil.
Right.
As is explicit.
And it's explicit like a static cast, not explicit like a braced initialization cast.
Yes.
Okay.
Because unlike a braced initialization, like you're actually saying, I want a conversion. Right. Whereas braced initialization might or might not convert anything. Right. Just the syntax.
I kind of like the fact that I have 3 different ways of spelling that right now. Because I can say braced initialization, narrowing, not allowed. Parens initialization, warn me if there's a narrowing. Or static cast, I am explicitly saying, I don't care if there's a narrowing.
Yes. So it may be that we want a way to say lossy.
Okay. Yeah. Thanks.
I'm going to try to take a few more. What's our hard stop time? I can't read that. Now. Well, let's take 1 or 2 more. I'm trying to get to Bjarne, who's third in line over there. Is that okay? I'll wait for people to wave at me. When you wave at me, I'll stop. Please go ahead.
So when you were talking, when you were showing the examples of the safe coercions that would be expressed as, most of those safe coercions don't exist in our code base because we don't like throwing exceptions. So other than the Anycast that returns a pointer, and I imagine there's also a version of as that does dynamic casts. So it seems like there's kind of exceptions are part of that, and then also there's potentially as hiding that different ases could have different performance characteristics, whether it's an optional or dynamic cast. So to me, it seems like your 2019 talk about zero cost dynamic cast and the new way, the kind of Swift-like exceptions would make this a lot nicer. And so do those seem dependent to you, or?
I don't think they're dependent, but they work well together.
Well, thanks.
And yes, for as, the static casts never will throw, but you are correct, the dynamic casts are dynamic, therefore they can fail. And they just currently pass through whatever the current spellings do. But that's why having is helps. Because as in the example I showed, you can say, if v is int, then v as int, and then you won't ever get an exception because you can test it.
Cool, thanks.
Hi, Herb. I have a question that I promise is friendly. I really like Circle. I think it's a fantastic tool. I think people could, as a superset, start building applications on it if they have control over their whole ecosystem. So my question is when is Visual Studio going to ship with Circle?
There's no plans for that. Circle is another compiler, and it's a great experiment, and I'm really impressed with the work that's been done on it. But it's a separate project at the moment.
So what I was going to ask you is also the idea for this one in Visual Studios, but it's already answered. But I also have another question: is like, can you in the inspect statement can you pass in two arguments and then have something like maybe if like inspect I and W and say if I is between 5 and 13, and W is true. Do some sort of same pattern matching code, or is that?
Yes, you can inspect multiple things. So if you, and I think both proposals do that, you can say inspect paren x comma y paren, and it treats it as if it were a tuple.
Okay, thank you.
Yes, thank you. Dave, then Bjarne, and then we'll wrap.
Okay. I think it's great that we're recognizing those 30-year complaints from people. And also that your rephrasings of those complaints are also valid and important things to look at. But I'm concerned about the rephrasing, if we really want to listen to people, I think it's important to actually catch the meaning. So one thing, I think you should go to Sean Parent's talk when he gives it, because Sean and I have been working out a definition of safety for C++, and it's actually like, to be consistent with how other languages use the term and whatever, it's completely orthogonal, right? Safety is about what happens when you do something wrong, not how easy it is to do something wrong, okay? So if people are saying too unsafe, I think we need to keep that, that meaning in mind. Another thing that I'm concerned about is the approach to complexity. You're not going to get to a simpler language by adding features, and I'm not saying the features don't make the language better.
I generally agree with you.
Even the spaceship operator did not make the language simpler. It made the specification smaller because you factored out a common thing, which is, great, but you expanded the language. There are now more things to know. Okay?
Just as a nuance, though, you are exactly right. And I tried to phrase it specifically. I did not claim it made the language simpler. It made the standard smaller. It made the language larger, but the standard smaller.
Yeah. So we can go on doing that, but let's just not fool ourselves. It's not going to address that problem of the language is too complex. And just my last thing from...
We're being told to move on, and I wanted to get a sentence from Bjarne if I could.
I'll just say we got a lot of mileage in Swift out of saying no to things.
Totally agree with that. Thank you, Dave. Bjarne.
This is, of course, a comment. I'd like to emphasize the idea of directly expressing things. And that's important. Is a direct expression, as is a direct expression. Now, there's a huge chunk of the C++ community that love complexity. They want every little detail of the implementation being obvious so that they know exactly how many nanoseconds it might cost. Sometimes I'm on that team, but 99.9% of the time I am not. And I'm suffering from the most programmers who can't figure out what things mean, who can't read the manual and make all of those bugs. Uniformity is great. So when I proposed that we should look at pattern matching about 6-7 years ago, one of the things I emphasized was that it could be used for unions, it could be used for variants, it could be used for dynamic cast, etc. And Herb's proposal is way beyond what I was hoping for. On the other hand, we have to be careful that the complexity doesn't creep into the things that are supposed to be simple to express. You can always do a reinterpret cast if you feel like it. And your the guys that reviews your code can comment whether it's reasonable. Sometimes it is, very infrequently it is. But notice, we got complexity over the standards committee. We got these redundant autos in concepts. We got 3 different interfaces to something that is fundamentally very similar, optional, variant, and
Any.
And any. We got complications to dynamic binding, which was explicitly part of the path to pattern matching. And of course, we have an endless number of casts. So could we try and encourage people to keep it as simple, as uniform, and direct as possible, and then leave the complications to code that we can already write today?
Thank you, Bjarne. We'll wrap it here. Thank you all for coming. Please enjoy the rest of the conference.